start our unit on binomial probability, we'll be looking at two key terms, a Bernoulli trial and a Bernoulli experiment. Now, we've seen these before when we looked at discrete probability distributions and indeed just looking at random experiments in Year 11. So a Bernoulli trial is just a single stage random experiment that has two outcomes. Now, 2 is especially important here. It's binomial probability for a reason. Bi is 2. So there has to be two outcomes. That's essential. Now, we can name those outcomes P and Q. I mean, we could name them anything we like. But if we say that they are P and Q, it's important to note that Q is just 1 minus P. So if we've got two outcomes, for example, we're tossing a coin, we could get heads or tails. They're the only two outcomes that we can get. We know that the probability of getting heads and the probability of getting tails must add up to a certainty, which is 1. And remember that all probabilities are numbers between 0 and 1. So if we have two of them, they need to be, if you like, complementary to each other where they add to 1. So anything that we have two outcomes with, say we're shooting at a target, perhaps we're shooting basketball or we're aiming darts, anything that we can have a success or a failure in, it could be something as simple as I'm going to check the mailbox. Either there'll be mail in there or there won't be mail in there. A success or a failure, those sorts of random experiments fit the bill to be a Bernoulli trial. Throwing a die, you need to be a little bit careful to actually just define your probability carefully. What is success? What is failure? Because as we know, when you throw a die, there's 6 possible outcomes on a standard die. So you'll need to actually state what the two options are that you're looking at. Perhaps you're looking at whether you get a 6 or you don't get a 6. Maybe it's, am I going to throw an even number or am I not going to throw an even number? And a hot tip is think of what success looks like and then put the word not in front of it to make sure that you've got two things that actually do add up to a certainty. So be a bit careful with that one. And anything that's got a yes-no answer, of course, can be seen as a Bernoulli trial. So define your P carefully. That's the probability of the outcome that you're considering a success, and the other probability will be 1 minus that. Now, the difference between a trial, which is just a single stage experiment, perhaps tossing a coin once, and an experiment is that the experiment says that we've got n stages. So perhaps we're tossing a coin 6 times. That would make it a 6-stage experiment. So it's an n-stage experiment where each stage is a Bernoulli trial. We're doing them repeatedly, and the probability of success, P, we've got a P and 1 minus P, so it's lots of these. And importantly, each stage has to be independent of the other stages. So something like tossing a coin lots of times fits the bill, because if we get heads the first time, that doesn't necessarily, well, definitely doesn't impact our chances of getting heads or tails on the next throw. The random variable x, now that's a big X, is what we consider the number of successes. So if I've, say, tossed my coin 6 times, then big X could take the value of 0, 1, 2, 3, 4, 5, or 6. Those are the possible values. Now, order is irrelevant in these sorts of experiments. So if I'm tossing that coin 6 times and considering how many heads I've got, it doesn't make any difference whether I've got 4 heads by getting head, 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 tail, tail, or whether it was tail, head, 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 tail. Makes no difference. We're looking at the outcome as though you've imagined running the whole experiment at the end saying, how many heads did you get? So order is not important in any of these questions. All right, now let's consider tossing a die 3 times, and we want to find the probability of getting a certain number of 6s. Now, we need to define our success. Let's let S be getting a 6, and N can be not a 6. Now, we can set out our understanding of what might happen in a simple tree diagram. And for simple experiments, this strategy is great. But what we want to do now is take our understanding of tree diagrams and the outcomes that they give us and extrapolate so that we can actually come up with a quick, easy method of calculating probabilities when we've got a lot more than 3 stages and we don't want to have to build a giant tree. So we already know that we can figure out the probability of each of our successes and failures. We make sure that they add up to 1. And of course we can write probabilities on branches, and we already know that you need to multiply probabilities together to get the chance of any one outcome occurring. Now, we can consider that there's 8 possible things that could happen in this experiment when we consider the order. But if order is unimportant, then there's actually only 4 things that could happen. We could get 3 6s, 2 6s, 1 6, or 0 6s. And that happens because here we've got a standalone outcome, and at the bottom we've got a standalone outcome that are not the same as any of the others. But these 3 that I've circled are actually all different ways that we could get 2 6s. we could either miss out on getting the 6 last, in the middle, or first. And these 3 here that I've put dashes next to are all the same when we don't care about order. All of them have 1 6 and 2 not 6s. So when we consider how we work out the probabilities, this is our old school way of doing it. And you can see here that there's one way of getting 3 6s, there's one way of getting no 6s, and there's 3 ways of getting 1 or 2 6s. Now I would like you to recall that if we expand something like this, a binomial expression, again by 2, p plus q, all raised to some power n, then we can find any one term with this simple recipe. And to remember what the whole expansion looks like, let's just say we have gone ahead and said, all right, we've got p plus q to the power of, say, 3. Then the whole expansion looks like 3 choose nothing, 3 choose 1, 3 choose 2, 3 choose 3. We always have those Pascal's triangle numbers first. Then we have the first part of the binomial expression raised to a big power, a slightly smaller one, a slightly smaller one again, down to nothing. And we have the second part of the binomial expansion raised to the power of nothing, then 1, and then 2, and finally 3. And then we have our signs in between. So this should be basic revision now, and we've got a method of cutting to the chase and finding any one term. Well, I've gone ahead and put these terms in here to show you that this is exactly what's happening when we use our tree diagram method. What we're finding here is that there was one way to get 3 6s. There were one way to get no 6s at all, but there are actually 3 ways that we could get 2 6s or 1 6. So 3 choose 1 and 3 choose 2 give us those numbers. And in fact, when we look at some example like, let's say this one, where we're finding the probability of 2 6s, there's 3 ways we could get it, but then we have to go along a path that has a probability of 1 6 2 separate times. So we need to multiply 1 6 by itself, and we're going along a path where we didn't get a 6, so we're going to need to multiply by 5 6 as well. And you can see that that can be more easily written as 1 6 squared 5 6 to the power of 1. So if we're finding the probability of 2 6s, we're saying, all right, that first thing, let's call this getting a 6. We want to do that twice. Then obviously we're going to need to have p raised to the power of 2. That'll give us our 6th multiplied by our 6th. And we need to get this, which is not getting a 6, once. So we'll need to multiply that by that as well. So we can cut to the chase and say the probability of getting 2 6s is going to be 3 choose 1, and then 1 6 raised to the power of 2, and 5 6, which is the probability of not getting 6, raised to the power of 1. Does that sort of make sense? Now, there's a little bit of flexibility here in this formula, which you probably noticed when we first studied it in year 11. And the flexibility comes about from the fact that 3 choose 1 and 3 choose 2 are the exact same number. 3 choose 0 and 3 choose 3, same number. So whether you call this 3 choose 1, and you're getting the 1 from being this number here, or 3 choose 2, and you're using that number there, it won't actually make any difference. And in fact, I tend to use one or the other each time. I don't deliberately memorize which one to use. In fact, I tend to think of my successes. I find what I want. I want 2 6s, so the chance of getting a 6, I raise that to the power of 2. I raise the other thing that I don't want to the power of whatever is left over. If we're doing 3 trials and I want 2 6s, I want 1 not 6. And then here, I can put either of these 2 numbers as my choose number, if that sort of makes sense. So here we're really just rolling together everything that we learnt in year 11 about tree diagrams and probability with everything we also learnt in year 11 about binomial expansions. And of course, the whole reason that we can even use a binomial expansion to find a particular probability is because of the fact that the 2 probabilities, which are the 2 numbers here in the brackets, they add to 1. And if you have 1 raised to any power, it will still equal 1, which means we can confirm that all of these terms definitely do add up to 1, and they have the same ingredients in them as the parts of our calculations when we were doing it using the tree diagram. But now we've obviously got a really powerful way of finding probabilities when the number here, which is the number of trials, is really big. Okay, an example now. I have found that I score a basket from the free throw line on average 3 out of every 4 attempts. If I shoot 20 free throws, find the probability I'll score exactly 7 times. Now, thinking this through, if I get it in 3/4 of the time, I'm probably expecting to score about 15 times. So if I've only scored 7, I've had a bit of a shocker. But we can find the exact probability by considering that I've got 3/4 of a chance of success and I have 1/4 of a chance of failure, and I'm throwing it 20 times. So any one term will be 20 choose something, 3/4 raised to 20 minus r, and 1/4 raised to r. So if I want to find the chance of getting 7 baskets, then I need to let 20 minus r equals 7, so r needs to be 13. So the probability of 7 baskets is going to be 20 choose 13, and here I could have actually used 20 choose 7, will be the same answer, 3/4 raised to the power of 7 and 1/4 raised to the power of 13. Now this is pretty unlikely, as you might expect. We were expecting that I might get a lot more baskets than that, but we can still come up with an answer on our calculator of 1, 4, 5, 4, and let's call this to 3 significant figures. Now that I've got this method, I can easily change my question and say, well, all right, I was expecting I might get around about 15 out of 20. What is the chance that I'll get 15 out of 20 shots in? Well, I find it easy to think, well, I need a 20 choose number here. I need to take what I want to get, the probability of what I want here. I want to get 15 of those, and I want to get only 5 failures. And now I can see I need 20 choose 5, or I could write 20 choose 15. And changing those numbers on my calculator there, I get a probability of 0.202 now to 3 significant figures. So we can see that that's a lot more likely. I've got about a 1 in 5 chance of that happening. So the expected value is not necessarily a certainty. We're still going to have all of those probabilities of everything that might happen. And we can see, I think, already that if we go to graph those probabilities, they're going to form something of a bell curve, because we're going to have the things that we're expecting or close to being a lot more likely than things that are far away from that expected value.